So right now we have a fun thing to show you. On the periodic table of elements under the metals category, you'll find an element called gallium.
It is a metal and it's solid, you can hit it. It seems to be solid as of now. However, it has a really low melting point.
Oh, what does low melting point mean?
Lower than 100 degrees Celsius actually. We could melt it by just sticking it into some boiling water and it'll actually turn into a liquid metal pretty easily.
That's awesome. So in the same way that ice is a solid when it's cold enough, all elements become solids when they're cold enough. Gallium becomes a liquid right around 87 degrees. And so what we're gonna do is we're gonna just take a pot of hot water. We're gonna go ahead and pour ourselves a pot of hot water.
There we go.
And we're gonna go ahead and melt our gallium. And the reason I'm melting it like this is because whenever you have hot air inside of a glass tube, it will expand. So we wanna make sure that our glass doesn't break. Any element that gets heated up is going to expand. Even the glass right now is expanding as we heat it up. Now, gallium is not dangerous. There's another element called mercury. You find a lot of mercury in thermostats, which is how we measure temperature. Now, mercury is very poisonous. It can be very dangerous if you have it without gloves on. Gallium, however, is much safer to work with. It can be pretty sticky, so I'm just gonna go ahead and pour it out onto a glove. So, 3, 2, 1. Oh, it feels like metal. It feels like liquid metal. I've never held a liquid metal before, and this is so cool.
Let me see. Go for it.
Right?
Yeah, I'm all in. Ooh. Yeah. It's definitely liquid.
We'll see if we can pour some.
Pour it back in?
Yeah.
There we go.
So gallium is a really cool element, as you can see. What's amazing about gallium is its super low melting temperature. It will melt almost at room temperature, which is crazy. Today we're going to be working with 5 different metals, and we're going to be putting them in hydrochloric acid to see how they react. We have zinc, iron, pure carbon, copper, and then we have tin.
Hydrochloric acid is a pretty strong acid. When we pour the hydrochloric acid in with a solution, it'll start to disassociate and the chlorine atom and the hydrogen atom will separate from each other, creating a strong concentration of hydrogen ions, and those will tend to react with a lot of different things, including human skin, which is why we're wearing lab coats, gloves, and goggles today.
Safety first, obviously. Yeah. All right, so we're going to pour 100 milliliters of hydrochloric acid in each of our mason jars. And then we're going to place the metal in them and see how they react.
So it doesn't look like there's a lot of reaction here with the tin. It seems to be roughly solid. It is bubbling a little bit around, but nothing immediate. Looks like the same can be said for our copper. Not a lot of bubbles attached to it at all. It's just kind of sitting there inert. Our square of carbon looks to have some bubbles attached to it, but also not any immediate dissolving.
Our iron seems to be really reacting. Look how much iron is reacting.
There we go.
This could be zinc chloride gas, or it could be hydrogen gas, or it could be water vapor. Definitely don't want to light this if it's that reactive. How did our zinc do?
Well, it's definitely reacting a little bit. I do think the zinc is attaching itself to the chlorine atoms and creating zinc chloride, and in that process, releasing a little bit of hydrogen gas.
And how is our copper doing?
Not a lot. It's mainly just hanging out. It seems like copper is that much of an inert metal.
And then our carbon?
It's reacting a little bit, probably really, really slowly.
All right, and then our showstoppers. So we have iron.
Yeah, it's definitely melting away.
Yeah.
Creating a lot of hydrogen gas and iron chloride.
We showed it reacting to zinc, and I want to show you guys real quick. We pulled it out a little early, but you saw, now this is all that's left.
That was after about 30 seconds to a minute.
Exactly, almost completely dissolved.
As you guys can see, aside from the copper, we had a slow reaction with the tin, a slow reaction with the carbon, and a quick reaction with the iron, and then a very, very, very quick
Very fast reaction, almost completely dissolved.
Yeah.
A very quick reaction with the zinc, almost completely gone after 30 seconds. So one of the most common magnetic elements on our planet is iron. And so we have a special experiment for you today. We have an iron mixture. It's called iron oxide, otherwise known as ferrofluid. Now, iron oxide is a little dangerous, which is why today we're going to be wearing gloves and we are going to be wearing safety goggles.
Oh yeah.
I'm going to put some in our petri dish right here.
This is a neodymium magnet. It's very, very strong. One side has a north pole and the other side has a south pole.
We're going to go ahead and show you. Ready? 3, 2, 1. Whoa.
So you can kind of see the pieces of iron in the iron oxide sort of aligning themselves in the presence of a very strong magnetic field. As you just saw, the iron in the iron oxide solution was able to suspend itself above the fluid and orient itself in the direction of the magnetic field.
You've probably heard that certain elements are very difficult to find, or some of them could be very rare, that when we do encounter them, it's kind of a big deal. Well, the good news is we can actually interact metals with different ionic substances in what we call a single replacement reaction. In a single replacement reaction, a metal reacts with some sort of compound, and when the two react, what ends up happening is a new metal is formed and a new ionic compound is formed. So let's take a look at 2 examples of how that happens. For this experiment, we are going to use copper 2 chloride. You may also use copper 2 nitrate. And then we are going to be using 2 different metals today. We're going to be using aluminum and tin. We do have an aluminum block here, but we can also use regular aluminum foil. I'm going to lay out both substances in these 2 small bowls. I also have a filtration set up on the side just in case I want to take this a step further after the reaction has occurred. Let's get started. So first we're going to place each metal in each cup, in each bowl, and then we are going to pour a little bit of this copper 2 chloride on our metals. So now we're going to interact the copper 2 chloride with both of our metals. And so notice how as I'm dropping copper 2 chloride on my aluminum block, we start to see some fizzing occurring. We're going to let this sit. Now we're going to observe what happens when we mix the copper 2 chloride with tin. For both setups, you want to make sure that you have enough of the copper 2 chloride to submerge both blocks in it. This will allow you to see the interactions happening between the copper 2 chloride and each of the metals. So what happens if you don't have access to metal blocks laying around? Well, the good news is you can try this exact same experiment with aluminum foil. So while we're waiting on these reactions to proceed and finish, we are going to try it out on a smaller scale with aluminum foil. You can use small strips of aluminum, lay it on here, just cubing it out there, and then we do the exact same thing that we just did, but this time we should be able to see the interactions right away because we're using a thinner piece of aluminum. We're seeing some bubbles form here. So we have enough that can submerge the aluminum foil in the copper 2 chloride. We've been able to observe the reaction of copper 2 chloride with 2 different metals. We did get to see it on a smaller scale by using aluminum foil and the copper 2 chloride. So if we really want to see the copper that's been formed from the 2 being mixed together, we can filter the mixture out. So I'm going to obtain my filter paper, place it nicely over my funnel, and then pour that mixture through the funnel, and let's observe. While we're allowing this to filter out, I am going to set this aside. And let's talk about the interactions that are happening in our bowls. So this right here was the mixture of copper 2 chloride and tin. Notice how you can see small little pieces of copper that are in the mixture. So notice how originally this is the color of our copper 2 chloride. We are now seeing a green liquid that has formed. Well, really what that green liquid is actually tin chloride. So the tin metal has reacted with the chloride ion in the copper 2 chloride solution. This green compound that you're seeing here is actually tin 2 chloride. And then if I pick up my block here, you can actually see that there has been corrosion, and that corrosion that you're seeing there is actually the copper metal. I'm gonna set this back. Now let's take a look at this mixture right here. So this mixture has the aluminum block and the copper 2 chloride. The exact same reaction that's happening here. It's just this one we're using an aluminum block. We started with a blue looking substance, and now we've got this blue, dark gray, cloudy liquid that has formed. If I pick up what was the aluminum block, you'll see that you've got more copper around this block in comparison to tin. Let's take a look. Now, why is that, you may wonder? Well, the reason why we're seeing more copper on the aluminum block versus the tin block is because of the fact that aluminum is actually more reactive than tin. There is what we call an activity series of metals where it describes and organizes the reactivities of different metals. If you were to access this activity series, you will see that aluminum is actually higher up compared to tin. And so that is why we're seeing more of that formation. I'm gonna set this back down, set this to the side, and let's take a look at what's happened here with our filtration setup. So notice how you've got greenish clear looking liquid. Let's compare it to what we had before. Now, what we're seeing here is the filtrate from the aluminum that has reacted with the copper 2 chloride. So this liquid in this flask is actually what we call aluminum chloride. Now, if I were to take this piece of filter paper off my funnel, now we've got some sort of powder here, and this is actually copper solid. This is what the copper would look like if we use aluminum foil, and then this is what the copper would look like if we use an aluminum block. Thanks for tuning in on today's experiment. We'll catch you again here at Expulsion Science.